Okay, let's go. We're talking about inequalities in a single triangle today. Now, we can use this in multiple triangles, but the big idea is each of these inequalities can only separately be used in one triangle, okay? So we have the exterior angle theorem, which really directly leads to the exterior angle inequality. All it says is, and we know that angles, for an angle to exist, it has to have a positive measure. If it's 0 degrees, there's no angle, and there's no such thing as a negative. So for an angle to exist, it's got a positive measure. And the exterior angle says if we add up A and B, we get the value of C. Again, that's just like the 180 minus A minus B, and then this is the linear, and it just ends up being that C is always equal to A plus B. We proved that, we used that, and so then that means then, if these are both positive numbers, well then C is the biggest, right? For example, we add up 3 and 2 and we get 5. Well, 3 plus a positive number equals 5 means the 5 is going to always be bigger than the A, and it's always going to be bigger than the C. And you're like, that's so obvious, Mr. Louis, but we're going to use it as a tool to go further. So yes, that's a simple little thing, and we're going to use it, and oh, it gets ever more clever. I love the rhyme of ever more clever. So don't you worry, it gets ever more clever. Okay. And then we use that to prove the simplified law sines. I call it the simplified law sines. I don't even think the book has a name for it. But the idea here is simply that in one triangle, you cannot say I have a triangle here and a triangle here, and because this is 60 and this is 50, that you know anything at all. Okay, so just to be clear, this is about in one triangle. But in one triangle, the smallest angle is across from the smallest side. Right? The little flashlight beam that doesn't open that wide is across from a little teeny side, a little tiny shine on the wall. But then you have a big angle, big flashlight, it opens to the biggest side. And then the medium angle opens to the medium side. And the converse of that. So if we know the sides, say for example, this is a 7, this is a 3, and this is a 5, well then we know this is the biggest angle because it's across from the biggest side. So the forwards and backwards, this is a biconditional. I call it the simplified law sines because when we get to trigonometry, we actually get a numerical relationship. And I mentioned this in a previous video, but it's a huge topic. And as we progress, we just get more and more information that we prove step by step. And so there is actually a mathematical function that tells you kind of the ratio or proportion between these. And we'll get to it. So that's enough. All right. And then the way you can connect more than one triangle is you use this or the exterior angle theorem to get an inequality. And then if you get two separate inequalities, like maybe this one you got from like the exterior angle theorem, and then you use that same thing in another triangle, or you use the little law sines here. Either way, you use two separate things or two separate triangles to get these inequalities. Then you can say, well, if A is bigger than B, right? So you're on the number line and you're saying here's B, and so A is bigger, so it's on this side, and B is bigger than C, so C is on this side. Well, that means A is bigger than C. I mean, that's actually the transitive property of inequality, which I'm going to mention right down below. But that's the big picture here, okay? Exterior angle inequality, which beyond this one day, this one lesson, we will not use that much. It's just a stepping stone that gets us this. And we will use the law of sines, or the simplified law of sines, to say smallest angle across from small side, medium across from medium, big across from big, in one triangle. I just want to emphasize that, because by far the biggest mistake is we get to problems like this where there's two triangles and somebody's like, well, this is 60 and this is 70, so I know this side is bigger than this side. And you're like, no. The 60's in one triangle, the 70's in another. They have nothing to do with one another. Okay, so just to be extra clear there on common mistakes. All right, you guys, so let's just dive into it, okay? Well, the first thing is I just want to define, there's a few definitions, because to do the proof, and I already wrote the proof, and we're just going to go through it quick, because I don't think it's super beneficial to go through. So the definition of an inequality of A is bigger than B simply means there's some positive number that I could add to B to get there, right? There's some positive length, right? For two numbers to not be equal on the number line, right? These are all the real numbers, then there has to be some distance between them. And so for A to be bigger than B, we just say there's some distance C between them. Okay, so that's it, right? So if, and then C has to be positive here, C is greater than 0, then A is bigger than B. That's the definition of an inequality, is they're not in the same location on the number line. Okay, all right, so there's distance between them. And then we have these. So comparison, it's also called the, I can't remember the name of it, but it's saying every pair of real numbers on this number line are either in the exact same spot, so they're equal, or it's bigger than B, or it's smaller than B. There's only 3 possibilities, right? When you have point B on the number line, any other number is going to be either on the right, the left, or in the same location. That's the first one. Transitive property, I mentioned it above, right? If you have A is bigger than B and B is bigger than C, you can chain them together and say, well, then that means A is the biggest out of all 3 and C is the smallest out of all 3. Now be careful with that one, and we'll get into a lot of examples down below where we use that. And then we have the addition property and the multiplication and division properties of equality. The main thing here is if you have a negative, it switches the sign, right? So if you have A is less than B and you multiply by a negative, the direction of the sign switches. And if I were teaching you algebra, oh man, I would dive into the Y. It's really cool. We could reverse the sides. I do things with my hands and I'm waving them. It's so high tech. But just remember that from Algebra 1. Oh, I wish I could just teach you all the math classes. And calculus too, it's beautiful. Okay, substitution property inequality is just saying if I have an inequality and I have something that's equal, I can swap it out, just like in an equality, right? So if A and C are the same, I could just erase this and put a C there. That's the substitution property inequality. Okay, so here we go. So the exterior angle theorem, that's really easy. We go, well, the exterior angle theorem says that, and then, the exterior angle theorem says that these two angles added up are equal to angle 4. We proved that. That's the exterior angle theorem. So we got that. And you could just take that from the diagram. You go, okay, I can state that. That's the exterior angle theorem. And then if this is true, and remember, every angle measure is a positive number, then we can just use the definition of an inequality and say, well, if we add a positive thing to it to get to A, that means B is smaller than A because we added a positive to get there. So we can literally say this sum right here means these two are both smaller than 4 because 2 smaller positive things added up to the biggest. So we say angle 4 is bigger than 1 and angle 4 is bigger than 2 by the very definition of an inequality. And that's it. That's the entire proof of that theorem. So we have the exterior angle theorem, or exterior angle inequality theorem, saying that this angle is bigger than either of the 2 remote angles. And now we're going to use that to prove the Cooler law sines theorem. This is just a tool, but it saves us a little work. Okay, so here's the theorem, one direction. So if one side of the triangle is longer than the other side, okay, so here's the given. We have a triangle, and we have, yeah, you can see it, and PQ is less than PR. Okay, so this one's smaller than this PR. No, PR is big. Yeah, PR is big, and PQ is small. Okay, that's the idea to start. So here's where we have to, I'm going to avoid going into the detailed algebra and inequality of this, but the idea is if this is smaller, that means there's some positive value I add to it to get to the bigger number, right? So they go ahead and give us this given that PN in this picture is equal to PQ. What I'm going to say instead is if PR is bigger and we're going PQ is smaller, that means that I could go PQ length and then add something to get to the bigger number. That's the idea. There is some number there that you add, and so we just put a point there, right? We just literally add the dot at that distance so that PQ and PN are the same because we knew PR was bigger. So we just lop off the congruent equal part and then leave the extra part because it's bigger. We leave that extra separate. That's all we did. That exists. By the very definition of inequality, we can add that point to the line segment. Well, we actually do the definition of inequality plus the betweenness and some segment addition, but I just didn't want to get into that. So we added that already. But really, that's an auxiliary point line we add. Okay, so now we know those two segments are the same. Well, what does that tell us? That tells us that the angles are the same, but by the base angle biconditional. So we have, oh, geesh, my Apple is getting so mad. Okay, so then these are the same by the base angle biconditional, okay? And then what does that tell us? Well, that tells us the angles are equal, and then we can combine that with over here. We say, wait, so we also know that angle 2 plus angle 3 is this whole angle. Just establishing that, right? That's just the angle addition postulate. Part plus part equals whole angle. And that also means then that the whole angle is bigger than angle 2. That's by the very definition of inequality, right? If you say 2 plus more is equal to PQR, well, that means PQR was bigger because we added a positive to get there. So measure angle 2 is less. Okay, so we got these two. We got measure angle 2 is the same as 1. And measure angle 2 is less than PQR, so we could substitute that in and say, well then, the measure of angle 1 is less than. So all we did was we replaced the measure of angle 2 here and here with the measure of angle 1. So we have measure angle 1 is less than PQR. Great, okay? So that was just substitution. So then we stop and we say, okay, this is the one that's harder to visualize. Measure of R is less than measure of angle 1. So up here in the picture, we're saying this is smaller than angle 1. Now part of you is like, okay, yeah, they took a step back, the flashlight got narrower, like right, if I'm here like shining it aside and then I step back further, then yeah, I'm a smaller angle. That's one way to think about it, but that's not like geometrically sound must be. So instead, here's a way to visualize it. Look at this picture right here. Angle R is one of the two remote interior angles, right? So this angle plus this angle are, just to make the picture a little bigger and clearer, these two, A plus B, add up to C. A plus B equals C. That's the exterior angle theorem. So that, remember, the exterior angle inequality says, oh yeah, so C is bigger than A and C is bigger than B because we added extra positives to get to C. So C was the biggest. So that just means angle 1, the exterior angle, is bigger than the remote interior. So okay, so we said that, and then we just chained those together. So angle R is less than 1, and 1 is less than PQR. So putting them together, transitive property, then that means measure of angle R is less than PQR. So is that proof going to be super useful for you? Not necessarily, but it is cool. Like, we can do this from the ground up with the systems we built, okay? Now that I say that, the converse is true as well, but it's harder to prove. It's a little stickier. So we would need, like, we would do basically the exact same proof, but the missing piece here is we don't have an exterior side inequality. Like, we don't have we could do all these other steps with angle addition postulate. Like, we could do everything else in reverse, but we don't have that key last step that says, like, these sides of this other triangle are longer. So we would need that theorem, or really common is the way people prove this is with an indirect proof. So that's actually the next step. And the exterior angle inequality, but for sides, that's actually what we do in section 5.5. So we'll get there. We'll do the inequality with side lengths. With two triangles, we'll do that. And then 5.3 is what indirect proofs mean, and I'll explain what they are and kind of show you, but I don't want to dive all the way into that rabbit hole, okay? It's really cool. We're actually going to skip that section in this class. I don't know which class you're taking this in years from now, though. All right, so an indirect proof is one of two things. We either say, or remember, anytime we have A implies B, that's the exact equivalent of the contrapositive, not B implies not A. So the first version of an indirect proof is we just prove the contrapositive. That's it. So you assume the not prove, right? So whatever it says is the ending, you negate it. You go, that's now the given. And then whatever was the given, you negate it, and that's now the thing you want to prove. So you're just negating the given and the prove and switching their places. And here we could actually do that. Again, I don't want to like introduce this and go down this rabbit hole, but just to show you, well, what's the negation of this? The opposite of being greater than is either being less than or being equal to. So really there's two cases. So the negation is PR is less than or equal to QR. That would be where we started. So that's two possible cases. We either have PR is equal to QR, or we have sorry, I can't write. So, or we have PR is less than QR. So we would start with one of these two and we'd say, can we get to the fact that, and our goal would be to get to the negation of the first one, and that would be that the measure of angle Q is less than or equal to the measure of angle P. So that would be the contrapositive. If we could prove this, then boom, theorem is proven. And so, well, let's look at it really quick. If PQ is this, or PR is the same as QR, well then these two angles are the same, right? So measure of angle Q equals measure of angle P, right? That's the base angle biconditional. Well, I wrote it in a kind of funky place. And what if PR is less than QR? So if PR is small and QR is big, well, we just proved that direction. We just proved that right here. We can actually use that then and say, well then, if that's true, that means this is a big angle, and that means this is a small angle. We just proved that. That must be true. We could do the angle proof because of that exterior angle inequality. So that would mean that measure of angle Q is less than measure of angle P. So putting those together, we do get this is true from this given. So we just proved the contrapositive. So we actually could do this. Now, again, I don't want to, I'll leave it there for you. So I don't want to get into that. Contradiction is actually a really cool way. That's the other indirect proof. And what you do is you say, okay, so we'll start with A. And then what you do is you go, let's assume the opposite of where we're supposed to finish, right? So if I say like, in this case, if I say, oh, yeah, we're starting with, and I'll erase this one because I'm doing craziness now. We'll start with this. And then what we go is hey, let's also assume the opposite of the ending. So PR is less than or equal to QR. Let's assume that is true. So that's not B. So we're saying we start with the given is true, and we start with the opposite of the thing to prove is true. And then what you show is it's impossible. You get something where like 1 equals 2. And you go, that's impossible. So these two things cannot both be true. It's impossible for both to be true. And then we go, so then if A is true, what does that mean? If A is true, and we can't have not B at the same time, that means B must be true. So it's a really funky kind of proof. Some mathematicians like argue against it, like it's not a real proof, and maybe there's loopholes, but it's a really cool kind of proof, and to this day it's still a really common way to prove this theorem as well as many other theorems in math. But we're not going to go into it. We'll just say this is true. Okay, so just to reiterate, going back up to the beginning, the big picture of this is we can forget the exterior angle theorem or inequality other than in this unit, which just says the exterior angle is bigger than either angle of the remote 2. And it just comes exactly from this. But the real nugget of this is biconditional small angle in one triangle is across from small side, medium angle medium side, big angle big side, and the converse is true. So that means if I start with triangle side lengths, then I know that, for some reason, it's not doing this. Oh well. If I start with the side lengths, smallest side means this is smallest angle, biggest side means biggest angle, biggest. So that's a biconditional. I can go from sides to angles or angles to side in one triangle. So let's just use it a bunch. Okay, here we go. Homework time. 17 minutes. That was good. Okay, but I'm going to do a lot of problems here. Okay, what is the statement below sometimes, always, or never true? So in triangle JKL with J is a right angle. Okay, so here's JKL. All right, and then it says if measure of J is twice measure of K, so if this measure is twice measure of K, well, that just means this is 45 degrees, okay, then the side opposite J is twice the length of the side opposite K. So is this always 2x to this x? No, that's not true. In fact, that's actually never true, and we could prove it later on, but if you just want to come up with something like, for example, let's do this. Let's solve this triangle right here. Okay, this is a cool problem. So let's start with this. If that's 45, what do we know? Well, the other one then, right? Because it just said if measure of J is twice measure, and we knew that J was a right angle, so we just divided by 2. So we subtract from 180. This is 45. So what does that mean? That means this is an isosceles triangle. So these two sides are congruent. So let's just come up with an example. Right? Here's 1 and 1. That's a number. Now we use Pythagorean theorem. We go 1 squared plus 1 squared equals c squared. That's 1 plus 1 equals c squared. So c squared equals 2. C equals root 2. Okay. Is root 2 2 times 1? No. Root 2 is root 2 times 1. It's 1.4-ish times 1. So it's definitely not always. And actually, if we just put any variable here, x, and solve for it, we go, okay, x squared plus x squared equals c squared. That's 2x squared equals c squared. So we square root both sides, and we get c equals square root of 2x squared, which maybe you aren't good at simplifying square roots, but the end result here is we get x times root 2. So actually, this is always root 2 times this side. So no, it is never twice as much. The big nugget there, so the answer here is never, but the big nugget here is the twice angle doesn't mean twice the length. It's not a direct proportion. It's a relationship that we'll get later. It's actually the sine of the angle is to the side as the sine of another angle is to the side. It's not a direct A is to A as B is to B, whereas if I multiply this by 2, I multiply this by 2. It's not a direct proportion, okay? Just that's the bigger idea there, but the answer would be never. Really cool problem. Okay, open-ended, draw a triangle ABC. Okay, here's angle ABC. And then side lengths of your triangle from greatest to least. Oh, okay. So it doesn't matter. I'm going to pick one. I'm going to say this is the big, this is the small, and this is the medium. So that would mean angle A, or measure of angle A, is bigger than measure of angle, I did medium was B. Oh, that's cool. Alphabetical is bigger than measure of angle C. Well, then what do the side lengths have to be? That means that AB is the biggest side length, which is bigger than the medium opens up to AC is the medium, is bigger than small opens up to AB. Wait. The big was down at the bottom. What the heck? I said big was AB, but that was not true. I pointed, right? I said big is pointed this side. That's BC. Silly, silly, silly. Okay. So the biggest was BC, and then that's bigger than AC, and the smallest opens up to AB. There we go. So that's, you notice the biggest side and biggest angle correlate. So angle A opens up to the 2 points that aren't A. It opens up to BC. Angle B opens up to the 2 points that aren't B, which is AC, and so on and so forth. Okay, Hector and Grace each labeled this. What's wrong? Well, here's what's wrong. This is bigger than this, and yet we should have 50 is bigger than 60. That's not true. So the triangle, the law of sines, as I call it, says the biggest angle in one triangle opens up to the biggest side, and the smaller one opens up to the smaller. So that's wrong. Whereas over here, we have big to big and small to small in this one triangle. Perfect. Okay, which angle are the greatest? So this is where we're going to use that exterior angle inequality. So remember, here we would have the measure of angle 1 plus the measure of angle 2, or 4, in this triangle right here, open up to the exterior angle are equal to the measure of angle 2. So I know the measure of angle, whoa, can't write angle. The measure of angle 2 is bigger than the measure of angle 1. I also know the measure of angle 2 is bigger than the measure of angle 4. Okay, do we have any other exterior angles here? Let's look, okay. Well, we got angle 3 here. Angle 3 is an exterior angle of this triangle. Okay, so that means the exterior angle is bigger than the measure of angle 5, and the measure of angle 3 is also bigger than the measure of angle 2. But hold your horses. Look at this. Look at this, okay? Angle 3 is also an exterior angle of this triangle. So we know that measure of angle 3 is bigger than this. So measure of angle 3 is bigger than, and then we can add those up. That angle is measure of angle 4 plus measure of angle 5. So it's bigger than both of them added together. And since they're both positive, that means it's bigger than angle 5, which we already had, and it's bigger than angle 4 too. Okay? And then we also have it's bigger than this angle. So measure of angle 3 is bigger than measure of angle 1. So measure of angle 3 is bigger than 1 and 2 and 4 and 5. So it's bigger than all of them. And then 2 is bigger than 1 and 4. Okay, let's go over here. So 1, 2, 4, greatest to least. So 2 is bigger than 1 and 4. So we have measure of angle 2. How do we compare 4 and 1 though? Oh, it just says which is greatest. I was going to say, I have no idea how to compare 1 and 4. We don't have the information. It's just saying which is greatest. 3 is bigger than 2 and it's bigger than 5. So 3 was the biggest in that one. And then the last one, 3 was also bigger than, so 3 was bigger than 2, 5, 3 is bigger than 1, 3 is bigger than 4, 3 is bigger than all of them. So 3 was the biggest. Whew, cool problem. All right, so use the exterior angle inequality to do that again. So all measures, well, let's just start, okay? So the only thing we know is exterior angles, but that's not one exterior angle. Here's one exterior angle. So measure of angle 1 is bigger than and it's the exterior angle of this. So it's bigger than the measure of angle 4, and the measure of angle 1 is bigger than the measure of angle 5 plus measure of angle 6. So if it's bigger than positive plus positive, that means measure of angle 1 is bigger than measure of angle 5, and measure of angle 1 is bigger than measure of angle 6. Okay, is it any other inequality there with that exterior angle? I don't see it. So now let's go to a different. That's the only triangle it's the exterior angle of. Okay, so now let's do angle 7. Okay, because this one says angle 7. So angle 7 is the exterior angle of this triangle. Okay, now notice, like, you might want to say that in this picture, angle 1 looks like it's bigger than this. But all you know is that these add to 180. It could be drawn not to scale. Actually, it could look like this and one smaller. So we don't know that. They add up to 180, but we don't know their relationship, how much that 180 is split up. It's tempting, though. Okay, let's look over here. Measure of angle 7 is bigger than all of the things it's exterior to. So it's exterior to this angle and this angle. So it's bigger than measure of angle 3 plus measure of angle 2. And measure of angle 7 is bigger than measure of angle 5 plus measure of angle 6. Okay, all right. Yeah, let's see that. I see that. Okay. Just double checking. Is there anything else? It's only the exterior angle of that one. I see that. Okay. And then all measures, or all angles whose measure are greater than angle 6. Okay. Let's just see if we can see anything else. I don't see anything else there. Okay. So if that's it, then angle 7 is bigger than all 4 of these. So that would be the answer for this one. Angle 1 is bigger than all 3 of these, right? So that would be for angle 1. And then all angles whose measure are greater than 6. All we have right now are angle 1 and angle 7. I don't see another exterior angle theorem, because knowing that this is bigger than something isn't useful, because we don't know how much of that angle is 1 and how much of that angle is 2. So we couldn't say like angle 1 is then bigger, because maybe it's not. So let's see, and I don't see any other exterior angles. So that's it for us. All right, let's go to the next one. This is where it really starts getting interesting. So this type of problem, I'm doing 4 of them because this is an awesome type of problem, okay? Now we're going to start chaining these together. So let's look at this. So in the left triangle, I'm going to label them as big, medium, and small using just B, S, and M, okay? So in the left triangle, this is the biggest. I'll do it in pink so it stands out a little bit more. So this is the biggest in this triangle. This is the medium, and this is the small, because smallest side, medium side, biggest side in that triangle. Okay. Now separately, totally separate question on the right. This one is the biggest because it's across from 18. This one is the medium because it's across from that one. And then this one is across from the smallest, 15. So this one is the small. Okay, so now we have 2 totally separate inequality chains here. So what we've got is, in the left one, we've got angle, WXY is bigger than, that's the medium, so it's bigger than the small. We should put measures, okay, is bigger than measure of angle. The small is WYX. And then that's bigger than, over here we have that's less than the biggest, which is measure of angle W. And then a totally separate chain is we have over here, the measure of angle, the biggest is ZYX, is bigger than the measure of angle, medium is ZXY, is bigger than, let's see, measure of angle Z. Okay, but the thing is we have no idea where these fall in comparison to this. So just think about this in terms of the number line. We have 3 points, A, B, C, or let's even relabel those to big, medium, small. But if we have 3 other big, medium, smalls, the biggest pink could be down here, medium, small, right? Or instead, maybe that's not the way it is. Maybe instead, all 3 are over here. Whoa, I used the eraser instead of the pen. I could have all the big, medium, and small pinks over here, or I could have any blend of them, right? I could have like the biggest here, the medium here, and the smallest here. So we have no idea how these two correlate unless we were given extra information. So it's common in like one of these problems, what will happen is we'll have some way to tie between these. So with side lengths, we do know this side reflexive is equal to itself, so we could start doing stuff between the two triangles. However, with angles, we have nothing to go on with these angles and these angles right now. Now, again, with the law of sines and trigonometry, you could actually find the numerical angle values right now. But all we have is this so far. And then you can answer all these questions up here, which is bigger, which is smaller. But notice that they all refer to the same things. So both of these, so they called this XWY. But notice both of these come from this chain of inequalities. And then XZ, they called this XCY instead of just X. But both of these come over here, XYZ. Where's XYZ? Oh, they just said it in reverse order. XYZ and XCY. They both came from that one. And then the first one, WXY and X, so then this one. So they only asked how do things in here compare and how do things in here compare. They are totally separate information. All right, let's do another one. This time though, we can maybe chain them together. Let's see. So first we got to complete the missing angles. So in this triangle, that's 140, so there's 40 degrees left over. In the inside, or in the middle triangle, this is also 40 degrees. Okay, and in this triangle over here, we have 55, 50, that's 105, so we have 75 degrees. So again, I'm going to use like my big, medium, small. I'm going to use just B, M, and S, okay? Well, look at this. In the middle, we have 40 and 40. So this, we know these are congruent. This is 100, so this is the biggest side, and then we just have two smallest. Okay, in the top triangle, we have, this is the smallest side, opposite 30. This is the medium side, opposite 40, and then this is the biggest side, opposite 110. Okay, and then over here on the right, we have this is the biggest side. Notice how it's the biggest side of this triangle, and yet on the other, in the middle, in this triangle, it's the smallest side. That's totally okay. All right, so that's the biggest side. Across from here is the smallest, and across from here is the medium. So I did a separate inequality for each triangle. So now let's write them out, okay? So this is all the information that we have here. We have, in the top triangle, we have BE is bigger than, AB is the medium, is bigger than, the smallest is AE. Okay, but then we have a separate chain, which is in the middle one, we have BE is bigger than, oh, they're both the same. So BC, which is equal to EC. Okay? And then the last one we have is, we have EC is bigger than, the medium is CD, and that's bigger than the small, which is ED. So the question is, could we tie any of these together? Okay, well notice, BE is bigger than EC, and BC is equal to EC, so we could take this over here that's equal to EC and put it over here. In this chain, I'm for sure that BC is the same as EC. Or I guess I should, hold on. I'll undo that. I'll copy it and paste it down here, and that's going to be in pink because we added it over there, okay? So we're sure that BC is equal to EC, right? We're sure of that, and we're also sure that BC is bigger than EC, so that we can add that chain. Now up here, here's where like it gets a little confusing. We know that BE is bigger than these, and we know that BE is bigger than these, but we don't know how those underlings relate to one another. There's no AB in any of this. There's no AE in any of this. So all we know, if we were to like arrange these in a chain, is these two separate things, right? But we have no idea how any of these other things on the right behave. We do know for sure that BE is the biggest side because it's bigger than every other side. We were able to chain two of these together, but the third we could not. So then we just look at the questions. So which one's bigger, AE or EB? So AE or EB, that's this bottom one right here that it asked for. So we know this is bigger. And then CE or CD. So CE and CD. So CE is definitely bigger than CD. And then BC and EC. BC and EC are right here, and so they're equal. So I circled the bigger ones on the top two and then said those are equal. So that's cool. Okay, couple more problems here. This is good. This is good. Okay, determine the relationship. Okay, so we're back to angles, which now this is the crazy part. We actually have to put together some exterior angle things, maybe in combination with it. So, whoo-wee, this is going to be big. Notice that back when we were in this problem with angles, we had no exterior angles, so there was no way to try and put the triangles together. Here, oh boy, we got our work cut out for us. So I'm going to pause really quick and get a drink of water as my throat is parched. Okay, let's hit it. Okay, so in each triangle, I'm going to label it. Here's my biggest. Across from medium is my medium. Across from small, here's my small. Then in the middle triangle, I'm going to say this is, oh wow, we could even do so many triangles here. Okay, so in this triangle though, this whole side's 17, and then 10 and 11. So what I know in the smaller triangle is this is across from 17, so it's the biggest, across from 11, okay? And then in this triangle over here, we have biggest, and then we have smallest, and we have medium, okay? Whew, let's zoom in there to make that happen. And then in the big triangle, I'm just going to double check. We also have that same relationship where in the double triangle, like in this whole thing here, just double checking, we have the biggest across from 17. We have this one up here, which is these two together, is the medium. And then we have the smallest over here across from 10. Here's the smallest. Okay, so we got lots of relationships here. Whoo-wee! Let's write it out. So we got measure of angle AKJ is bigger than measure of angle. They never called it A, so I'm going to call it JK. So, oh, sorry, the medium one in that top triangle is measure AJK. And that's greater than the measure of angle JK. All right, then totally separately, we have the middle triangle. The measure of angle JSY is bigger than the measure of angle JYS. And that's bigger than the measure of angle SJY. Okay, and then in that small triangle to the right, we have measure of angle, they should have just used M, but okay, JMY is bigger than measure of angle, that was the biggest, so JSM is the medium, and then we have measure of angle, the smallest, MJS. Okay, and then we even have the big double triangle there, JMY. So in that triangle, we have the biggest is JMY. And that's bigger than the measure of angle, the medium is YJM or MJY. And that's bigger than the smallest in that triangle, which is angle Y or JYM. Okay, now that's just the four triangles. That's using one set of inequalities. Now we got to look at exterior angles, but we only really have two exterior angles as I see it. So the two exterior angles is this one's an exterior angle of this triangle. So we can say it's bigger than the two remote angles. And then we have this one's an exterior angle of this triangle. And those are the only two I see. So it's not going to be so bad. So let's write those. So measure of angle JSY, right, is equal to the sum of the other two. So it's bigger than the two remotes. So JSY is bigger than, that's JMY. JMY. And then measure of angle MJS. All right, and then the other side, so JSM. So the measure of angle JSM, that's remote to this triangle. And so it's bigger than JYS. And the measure JSM is bigger than SJY. Whoops, I wrote it wrong. SJY. Whew! Now chaining these together would be a mighty task. Like for example, I would notice that this top one on the right, I could take that and say, well, if JSY is bigger than JMY, then I could put it right over here at the front of this, right? And then you could keep looking. You could be like, well, oh, and I could put it on the front of this one up here. And things are bigger than JSY. So anything bigger than JSY? No, I don't see that over there. Yeah, I know this is tough trying. This would be a lot of pairing together to try and rearrange. But let's just see if we can answer the questions as is. So what's the relationship? We didn't have any equals that we saw. So KAJ, that's this one right here, and AJK, oh, AJK was bigger. All right, so 30 MJY. So MJY came up a lot. So MJY came up here. Is that going to answer JYM? Oh, it's bigger than JYM right next to it. So MJY was bigger. SMJ. So SMJ, let's try and find that one. SMJ. Oh man, this is hard. SMJ. Where's SMJ? How am I lost here? I don't see it. What is SMJ? Let's look at SMJ. Where's SMJ? Is in this triangle. So it's twice. And so I did JMS is what I called it. Did I not write that one? Did I mess up when I wrote that? Hold on one second. Oh my gosh. It took me a second to realize SMJ. They're just labeling it different. It's not the same letters. I called it JMY. So that's this angle, is that's that same angle. So how's that one relate to MJS? Oh, this one's bigger. The JMY angle is bigger. I used different points. I was like, how did we never come across this angle once? Okay, so let's look at AKJ. So AKJ is on the top, and JAK, oh, AKJ is bigger. And then MJY, or MYJ, sorry. MYJ is this angle down here. And that's bigger than that's smaller than JMY. So JMY is bigger. And one more, JSY. So we'd never even use the exterior angles. They were so nice. Okay, so JSY and JYS. JSY is bigger than JYS. Oh my gosh, JSY. So they never even had us. We had so much more information we could have given there. All right. So now let's really use it though. This is when it's sides, because then they're reflexive equal to each other. That's when things get interesting. So let's really dig in here. All right, so we can solve for a lot of this. If that's 91, here's 89 degrees. Then in this right triangle, let's just solve. So that's 130, that's 140. So this is 40 degrees. Okay, and that's 95. That's 66. So in this triangle right here, we have 66 plus 89. That's a total of 140, 155, I think. So that's 25 degrees. Okay. Even if it's not 25, it's close. All right. Oh, and then we got to get in the middle here. So 95 plus 45, that is 140. So this is a 40 degree. Now remember, trick. These have nothing to do with one another in terms of this triangle side is equal to this triangle side. Actually, they do have something to do with each other. What's that thing they have to do with each other? Alternate interior angles are congruent. So this line is parallel to this line. Does that matter? No. But like, hey, we found something interesting. So now let's go ahead and label sides. Okay, so I'm going to do green here. I'm going to say in this triangle, this is the big, this is the medium, and this is the small. In the middle triangle, this is the big, this is the medium, this is the small. And in the right triangle, this is the big, this is the medium, and this is the small. And now we can go ahead and put those all together. Let's see what we got, okay? Putting these together in the first triangle, we've got, I cut off the top, I'm assuming that's a Z. So we've got ZY is bigger than, oh, it's easier to write this too, you don't have to measure the angle over and over, is bigger than ZT, which is bigger than TY. Okay, then separately, I'll put it off to the side. We have ZR is bigger, well, I was going to say equal, is bigger than ZY. And we have that's bigger than YR. And then the last one, I'm just writing it on the left because I have space there. We have ZR is bigger than RS, which is bigger than ZS. Okay, so the question is, can we tie these together? All right, well, let's find any commonalities here. The two commonalities are these two that they share. So ZR is the biggest here. So we know ZR is bigger than all of these things. That's pretty cool. That's useful. It's just huge. We don't know how it relates to the leftovers over here. So that's totally separate, right? We don't know that one. Okay. Well, actually, we do know ZR is bigger than ZY. So we do know it's bigger than this. Oh, sorry. We do know it's bigger than this. Oh, so actually ZR, because it's bigger than ZY right here, so that means ZR, copy, is bigger than ZY. We can put it right here. ZR is actually the biggest out of all of them. Whoa, look at that, okay? So we can put that right there and change it to be pink. There we go. So we can add that because it's bigger than ZY, so it's bigger than all of those. It's bigger than all of those. ZR is the biggest flat out of all these. Oh, that's interesting. Okay, is there anything else we can combine? I like combining things. So we got ZRs. What about the ZYs? Oh, that was the only other thing we had. Oh, okay. Anyways, then let's go on. So which one's bigger, ZY or YR? So ZY or YR? Well, that's this last piece over here, so ZY is bigger. The next one is SR or ZS. Oh, SR, that's this first one right here. So SR is bigger. Which one's bigger? RZ, that's over here, or SR. Oh, RZ is bigger. Oh, we're not doing any chaining together. Okay, so ZY or RZ. Oh, that's this one right here, or this one right here. So ZR, which is the biggest out of everything. Okay, that's right here. And then TY or ZY. So TY or ZY. So ZY is bigger. That's this right here. So ZY is bigger. And then lastly, which one's bigger, TY or ZT? That's this one right here. So ZT is bigger. Shoo! Okay, so let's do just one or two proofs. I think I did two proofs really quick. Okay, so here's a proof using inequality. So we're starting with PR is the same as QR. Okay, so let's just say that's given. Let's do it in blue. Okay, so PR is congruent to PQ. And that's given. And then that leads to the base angles are the same. So that means angle R is congruent to angle Q. That's the base angle biconditional. Okay, and that leads to measure of angle R equals measure of angle Q. Okay, that's the definition of congruent angles. Okay, so now that these angles are the same, and we're given that this is bigger than this, well, how are we going to use that to get that the angles are bigger? Well, let's use this over here to say, well, we're given QR is bigger than QP. That was given. And then we could use that like law of sines, right? So we were just doing over and over and over. So if QR is the big and QP is the small, that means that this is the big angle compared to small angle. So that would tell us that measure of angle P is bigger than measure of angle R. Okay, and that was, I'll call it the law of sines, just because that's what we'll call it later on. It's not actually, I don't know, let's call it the baby version of the law of sines. That's good. Okay, so if P is bigger than R and R is the same as Q, well then you could just use substitution to say, well then that means the measure of angle P, which was already bigger than R, is bigger than the measure of angle Q, which is where we wanted to go anyways. So that's the very substitution property inequality. Wow. Okay. Woohoo! All right, so down here, I put just a little tidbits here. This is a harder proof, so I just wanted to show you. I don't think this is on the homework. Okay, so we start with JM and oh, it's given in the diagram showing you so which segments are congruent. Okay, so let's start. What do we want to do? Well, first, we want to show that angle 1 is bigger than angle 2 in the end. So let's get an inequality with angle 1. Well, we know the measure of angle 1, whoa, that's not an angle, measure of angle 1 is bigger than what? It's bigger than, it's an external angle, so it's bigger than the measure of angle K, right? Or you could say it's bigger than the measure of angle L, or not L, KLJ as well, but because I already circled this little hint to myself, okay? So we're going to do this, and that's the exterior angle inequality. Okay, so what could we do with that? Well, we know the base angle theorem too. The base angle theorem says, and I'll put this to the side because we're going to use this. All right, we're also going to say, well, because KL and JL are equal, so we have JL is congruent to KL. Okay, well, that told us that that the angles are congruent. So we know angle K is congruent to angle LJK. LJK. Right? And so how are we going to use that though to get the angle 2? Well, the way we're going to get that is by using the isosceles triangle on the right. Okay. Oh, and so sorry, this was the base angle biconditional. Okay, so we're going to put that off to the side too. And now we're going to say, well, because the other things were congruent, we had JM was congruent to JL. All right, so if these are congruent, that was the given. Then again, we do the base angle biconditional. So we get measure of angle, or not measure, we just get angle 2 is congruent to angle M, and that was the base angle biconditional. Okay. And now we could separately say we have the exterior angle theorem, which says, this is bringing in 4 separate tracks of logic here. This is really cool. So the exterior angle theorem, not inequality, says the measure of angle 2 plus the measure of angle M equals the measure of angle, what is it, LJK? Okay, that was the exterior angle theorem. All right, and then now you're starting to see maybe how this comes together, right? So we have this measure of angle K. Over here we have this LJK. We're starting to gonna put these together, okay? Let's do that. So let's go this and this together. We'll substitute. Now technically, actually, we should have done this goes to the measure of angle 2 is equal to the measure of angle M by definition of congruent angles. Okay, so now we can substitute this together and we can say, this means we got measure of angle 2 plus measure of angle 2 equals the measure of LJK. That was just substitution. Prop equality. Okay, and then over here what we can do is just put all these inequalities together. So let's bring them together, okay? So what does this one mean? Well, if these two add up to be LJK, that means the measure of angle LJK is bigger than the measure of angle 2. That's the very definition of inequality, right? So this proof is harder than I would absolutely expect of you on a quiz or test, but you can follow along with all this logic. So we've got LJK is bigger than 2, and we're going to just bring these down. Okay, let's go. Bring this down, okay? So bringing this down, because those sides are the same, we get those are the same, and then what we can do is put those together and say, all right, well, we can substitute that in. Now, okay, technically we should say measure of angle K equals measure of angle LJK, just by the definition of congruent angles. Okay, so now that we've got those are the same, we could just substitute and say, well then, that means we have the measure of angle K, which is the same as LJK, must be bigger than the measure of angle 2. Okay, so we got that. That's just substitution. And now we can bring in the other thing that we got, substitution, prop equality. Okay, oh, inequality. Okay, and now let's just go up here. And now we have that exterior angle theorem that said 1 was bigger than K. And so if 1's bigger than K, oh, my pencil, go for it. Okay? If 1's bigger than K, and K's bigger than 2, well, then that means the measure of angle 1 is bigger than the measure of angle 2, and that's the very transitive property of inequality. Woo! That was a long video, you guys. Okay, so big idea is just big across from big, small across from small, medium across from medium in one triangle. That was a 54-minute video to cover that one big idea. Oh, I hope you enjoyed it, guys.